On lab 4, we're going to be talking about the motor drivers and inverse kinematics. We'll walk you through how to operate your motor drivers and motor wheels and through the basics of inverse kinematics. In addition, we're going to be talking about what the difference is between the inverse and forward kinematics. The motor wheels of the scuttle requires powering the beagle bone and the motor driver using the battery pack. This means that in this lab we're not going to be using the 12-volt power supply that we gave you on lab kit number 1. By the end of this lab, you will understand how your local chassis variables x dot and data dot get transformed to individual wheel speeds using inverse kinematics, which then get transformed into a PWM command that the drivers can understand. For lab 4, it's very important to review the reference documents, in special the wiring diagram and the scuttle kinematics. The wiring guide provides guidance on how to connect all the hardware components to the beagle bone. In this case, we're going to be using the motor driver signal cable slide, which provides information on how the beagle bone is connected to the motor driver and how the motors are connected to the motor driver as well. The scuttle kinematics guide provides the following. It explains the robot geometry in terms of the radius and the length, the wheelbase. It talks about the imported variables such as phi, x and x, y and data. And it talks about the kinematics of the robot, that being forward and inverse kinematics. During this lab, we'll be using the inverse kinematic equations, and these equations, the input for it is the chassis linear speed, so x dot, and also the chassis angular speed, data dot. And with these constants, we'll get the individual wheel speed phi L and phi R. This will indicate the angular velocity of the left wheel and the angular velocity of the right wheel. If you go to your lab kit PDF on eCampus, you will see that lab kit number 3 has been added to the PDF, and this includes the scuttle frame with the encoders, the motors, the skate wheels and the caster wheels, in addition with the motor drivers, all the cabling for the drivers and encoders, and the I2C encoder board. Now let's move on to task 1. This is about wiring and running the scuttle motors. This figure 1, shows the way the wires should be arranged to connect the beagle bone to the driver and the motors to the driver. We will be giving you the scuttles during the lab session, and we're gonna be giving it to you as it is in the screen, just with the driver and the frame. The first step is to place the battery like this. Make sure that all your batteries are the correct orientation. Then connect the beagle bone blue using the male barrel plug to Anderson connector, and then you can connect the cable that's going directly to the driver. In the case of the video, my driver power cable goes through the frame. That's why you cannot see it. The next step is to connect the signal wire. The easiest way to do this is to grab the 4-pin DuPont female connectors and plug it into the driver board as shown in the video. Then grabbing the pair of cables that matches with input 1 and carefully placing it into input 1 motor driver. Then grabbing the other cables and connecting it to the input 2 of the beagle bone blue. After everything is connected and the TA have given his approval, we need to prepare the L1 motors.py file to be executed. So first we need to boot or power up our beagle bone using the battery pack and do the standard procedure. Connect to its Wi-Fi, then open Cloud9. Make sure you are connected to the Wi-Fi network, and then download from the GitHub Basics repository the L1 motors, L2 speed controls, L2 inverse kinematics, and L1 gamepad. All these files will be downloaded to your basics folders using the wget command. The basics folder should contain all the previous files that we have used on the previous labs. Then we're gonna be lifting the scuttle frame using the 3D printer stand that we have. So make sure you have one of these in the back of your scuttle. This is so the back wheels are elevated when we power up the wheels. Then we're gonna go to Cloud9 inside the basics folder. So here we go to the basics, and we're gonna type sudo Python 3 L1 motors. So the expected output should be, if we go to the while loop of the L1 motors, we can see that being commanded to do is to move the left wheel at a duty cycle of 0.6 and the right wheel at a duty cycle of 0.6 as well, then waiting 4 seconds and going in reverse doing the same time. Back in the terminal inside the basics folder, we're gonna type sudo Python 3 L1 motor, enter, and now it's gonna be move forward for 4 seconds and then move back for 4 seconds, and it's gonna be on an infinite while loop until we Control C after the second reverse is done. Task 2. Perform inverse kinematics. All the driving commands of the scroll will come in the form of x dot and data dot. X dot being the velocity of the chassis, and data dot will be the angular acceleration of the chassis. During this task, you will demonstrate how x dot and data dot values get converted by the L2 programs into individual wheel speed. Before continuing, I recommend to link to get a better understanding on how the inverse and the forward kinematic works. Here in the lab, we use kinematics to describe the motion of the scroll. We use forward kinematics and inverse kinematics to go back and forth between individual wheel speeds and frame linear velocity and angular velocity. As shown in the screen, we can see the forwards and inverse kinematics. The forwards uses the individual wheel speed to calculate the chassis velocity and chassis angular velocity. In addition, it uses this predetermined matrix that uses the constants R and L. L being the distance from the middle of the robot to the wheelbase, and R being the radius of the wheel. Inverse kinematics does the opposite by converting the linear velocity of the robot and the angular velocity of the robot, of the chassis, into individual wheel speed. In case you need a reminder, positive x dot is this way and positive data dot is. In addition, we use the right hand rule to determine the rotational direction of the wheels. So when the wheel rotates counterclockwise, you got a positive by L, and when the wheel rotates clockwise, you get a negative by L value. If you input a positive x dot value, such as 1 meters per second, and as data dot you input 0 radians per second, you will get velocity on the wheels, a positive velocity on the wheel. Okay? If we put a negative linear velocity and again 0 as my data dot, we'll get a negative wheel speed. If we input a 0 linear velocity and something, let's say use a positive data dot, we'll get something like this, where we have a negative value on our left wheel velocity and a positive value in our right wheel velocity. And this is because we are just doing pure rotation along the sea with a positive angular velocity. And the same thing happens if I have zero linear velocity and a negative angular velocity. We will get the opposite. We'll get a positive left wheel speed and a negative left wheel speed. For the second part, we're gonna simulate a navigation path that's shown in figure 2, and we're gonna make the robot drive it on the air, meaning that the wheels are gonna be unloaded. Note that the scuttle's max speed is 0.4 meters per second forward, so keep that as a constraint for your calculations. For this task, you need to choose your own D1s and D2 length, D1s and D2, and your scuttle will begin in the green star and end at the red star. In order to finish this entire circuit, the scuttle will need to do 9 motions. First, we'll have to go forward, both wheels going at the same speed, stop at the corner, make a point turn, and this is where the linear velocity is 0 and just we have a velocity, an angular velocity. That's motion 2, and then straight down. That'll be motion 3, and then you can keep going and counting until we get the final motion 9. You will calculate each motion, linear speed and angular velocity, and also the duration of the motion. Then you will put it and complete table 1. You will write your own script using the following link as a lab template, and this will be a level 3 code. By following the link, we will see the lab 3 template, and we're gonna use this template as our lab 4 template. Once you download it into your basics folder, you'll fill it out, type your team number, and your team members. So you can choose the hardware person, the person that it's present in the lab, and the software as the person who's virtual, the date of the lab, and what's the purpose of the script. Also indicate D1 and D2 distances. This is for us so we can double check that you did the calculations right. In addition to commenting the code, you will need to modify a little bit. So each block represents a motion, and the input arrayed for my velocities are not your wheel velocities, but your x dot and data dot. So that's what we refer as a pair. This time that slip represents the duration of your motion. So if you have 9 motions, you should have 9 blocks like this. Task 3. This for sure will be the most fun we're gonna have in the lab. Once you're ready, please ask a TA for a gamepad and a Bluetooth dongle. Then you're gonna run the command ls usb. In the terminal, we'll type ls usb, and this will show the devices connected to our USB bus. And now I don't have anything connected to it. After placing the USB in the USB port, I'll type ls usb again, and I'll see something else. That means that our Bluetooth dongle for communicating to our Xbox controller. I'm gonna turn on the controller by pressing the middle button in the gamepad. Then I'm gonna run the program by typing the command sudo python 3 lab3 underscore gamepad control.py. Hit enter. And then if your controller is well configured, it should react to our input. Finally, you will have to comment the lab3 underscore gamepad control code. So basically going through each line and adding a comment on the side explaining what each line does. In addition to explain the flow of the data from the moment it's read from the joystick to when it's outputted to the motor driver. And make sure to include this information in your lab report. For the post-lab activity, these are the things that we're going to be looking for. In addition, for a little task that we have for you, which is going through this link and learning a little bit about NumPy. And we're going to have a quiz at the beginning of next lab. That'll be next lab 5. And your code will need to be submitted with your lab report. So make sure you include your L3 code. And remember that the lab report is individual.